All right, calculus class. We are moving into what becomes probably one of the more difficult sections of this course, and that is some variety of integration techniques. Now, we've already done one of the integration techniques, which is just basic integration, where we are reversing the power rule, adding 1 to the exponent, dividing by that number. Now we want to move into two other integration techniques. One is called integration by substitution, which we're going to talk about today. And then secondly, early next week, we'll talk about integration by parts. Now, these are not the only two ways to integrate. There's a couple other ways to integrate, but we will leave those for your university professors to discuss when you get there. All right, so integration by substitution, and we're going to get a little tricky here. So what we're going to do first is we're going to look at an example that we would have done in our derivatives unit. All right, so here we go. Find dy dx if y equals the square root of x squared plus 1. So let's find the derivative of this function. Now, this function is a composite function, right? It's the square root function, it's the quadratic function x squared plus 1. It's a composite. We have the square root inside the radical. So when we take the derivative of a composite function, we use the chain rule. So here we go, using the chain rule. Remember that this is x squared plus 1 to the power of 1/2. We're going to pull that 1/2 out front, times the quadratic to the negative 1/2, and then we're going to take the derivative of the inside of x squared plus 1. The derivative of that is 2x. All right, then we're going to simplify. We have 2 divided by 2 cancels out. This x is in the numerator. This is a square root of x squared plus 1 that is in the denominator. So we get the derivative. There it is. Okay. Now, our goal with the substitution rule is to reverse that. So, turning it around, we're going to do that in a minute. I'm going to show you this blue stuff here behind me is the way we're going to turn it around. But let's go look at the general rule for integration by substitution, and then we'll come back and finish up the example behind me. Okay, here's the general rule. So, and again, with general rules, it's great if you can understand them, but if you can't, that's okay too, because what we really want to be able to do is use the rule. And so if you don't get this, hopefully when we go back and do that example and then do a couple more examples, it'll all start clicking and you'll see how it works. But here's how it works in general. If we're finding the derivative, d dx, of a composite function, f of g of x, right, we take the derivative of the outside, so f primed of g of x, times the derivative of the inside, right? So that's our chain rule. Now, turning that around, we want to take the integral of our f primed g of x, g primed of x, dx. And that has to equal the original function, right? So it's just, we went forwards, now we're integrating this and getting this. Now we're going to add c because, again, we don't know what family of functions this is a part of. All right, so this is our general rule. Now, often with substitution, in substitution, we're going to make a substitution in order to make things simpler. And you'll see that when we do the example. So we're going to change the variable x to u. And we're going to let u equal g of x. Remember that g of x was the inside function here. Okay? So we're going to let that inside function equal to u. Then what happens is our rule becomes the integral of f of g of x, g primed of x, becomes the integral of f of u du. And f of u du is no longer a composite function. F of u du is just a function that we can use our general integration that we were doing the other day to integrate. Okay? So this in the box here becomes what is called our rule of substitution. Okay, we let g of x equal to u, and we make the substitution, and then it becomes a simpler integration that we can do using what we already know. So that's the goal. As the goal is all mathematics, is to reduce a problem into something that you already know how to do. Let's go back to the other board and I'll show you how it works with that example. Okay, so over here now what we have is we're reversing this, and I hope you can see this. Hopefully it's dark enough, but we have the integral of our x over the square root of x squared plus 1 dx. Okay? What we're going to do is we're going to make a substitution. And what we're looking for is we're looking for an inside function. Okay, so we have the square root of x squared plus 1. that makes x squared plus 1 an inside function. It is inside the square root function, okay? So we're going to let u equal x squared plus 1. Perfect. If we let that happen, what happens is when we take the derivative, we're going to get 2x dx, right? So u equals x squared plus 1, du equals 2x dx, right? 2x and then times the derivative of x. Again, treating it as a chain rule or implicit differentiation. Okay? All right, so what we're looking for now is in the numerator of this question, we have this x dx. And when we take the derivative of our inside function that we let u equal, we are going to be looking for that same piece. Okay, so we let u equal x squared plus 1. We took the derivative of it, we get 2x dx. This x dx is what we're looking for here. Now the number doesn't matter because the number is just a constant. And when we integrate a constant, it just comes out front here and we leave it out front and we integrate without the constant. Constant just gets multiplied in at the end. All right, so what we're going to do here then is we're going to divide by 2 and divide by 2 so that these cancel out. We get du divided by 2 equals x dx. Okay, now we're going to make our substitution. So here now I've made our substitution. The numerator, which was x dx, is now du over 2, right? X dx equals du over 2. There it is. The denominator, which was the square root of x squared plus 1, now becomes the square root of u, because u equals x squared plus 1. Okay, let's simplify this a little bit. Let's pull this, there's a factor of 1/2 here, 1/2 du. We're going to pull that 1/2 out front, and that's going to leave me with 1 over the square root of u du, or 1/2 integral u to the negative 1/2 du. And at this point, this function here, this integral, is a simple integral for you to do because we've done lots of them over the last couple of days, like this, right? We keep the 1/2 out front. The integral of u to the negative 1/2 becomes u to the positive 1/2, add 1, divide by the 1/2 plus c. Simplify this a little bit. We have a 1/2 divided by 1/2, cancels out, leaves me with a u to the 1/2, square root of u, plus c. But we can't end there, we have to reverse the substitution we made in the beginning. In the beginning, we substituted u for x squared plus 1. We want to reverse that substitution at the end here now. So instead of root u plus c, the answer is root x squared plus 1 plus c. And again, that's where we started with, right? Our original function right here was y equal to x squared plus 1. And here we got it back. Okay, let's try another example and see if this works. So here's another example. Let's say we are asked to find the integral of x squared minus 5 to the 8th power times 2x dx. When we look at this, initially we realize we cannot use just our normal integration rule where we'll add 1 and divide. That will not work for something that is a product. Okay, so what we're going to do is we're going to use the substitution rule. And so to use the substitution rule, we're looking for an inside function. Well, we have this quadratic function, x squared minus 5, inside a function that is to the power of 8. So we are going to let u equal the inside function, x squared minus 5. We're going to take the derivative of that function, du equals 2x dx. Okay, now we're going to look and see. We're looking again for a substitution. Well, here we have 2x dx. Here we have 2x dx. Now again, the numbers don't matter. We can always pull the numbers out front, but because we have an exact replica here, we have 2x dx and 2x dx, we can just substitute the constants out and they will disappear. So we're going to make our substitution now. So the original question becomes the integral of u to the 8th right? X squared minus 5 is u, and then the 2x dx is du. This is now an integral we can take. It becomes u to the 9 over 9 plus c. Reverse the substitution, and we are all done. And there we have our original function right here. And again, if we looked at this and we wanted to take the derivative of this, you would multiply this 9 out front to cancel these out to the power of 8, and then times the derivative of the inside function, which is 2x. Right? So you can see that it will go back and forth now using this. But again, we substitute so that this integral becomes something simple that we can do, that we've been doing for the last while. All right, so again, to start, we're looking for an inside function. We're letting u equal that inside function, taking the derivative of u, and then seeing if we can make the substitution. And it's really important that it's the x dx that we're looking for. The numbers don't matter. If the numbers are the same, great. If the numbers are different, we'll pull them out front. Okay, we'll do one more example on the other board, and then I'll give you your assignment. All right, here's one more example. This one's got some trigonometry in it, which shouldn't be a problem. So we've got find the integral of 2 plus sine x to the power of 10 times cos x dx. Again, we're looking for a composite function, and we're looking for the inside function. So right here we have that. We have this sine function inside a power of 10 function. So we're going to let u equal the inside function, 2 plus sine x. Now we're going to take the derivative of that. So du equals the derivative of 2 is 0 plus the derivative of sine x, which is cos x dx. Okay, and again, what we're looking for is this, and there it is. We have it. All right, let's make the substitution. It becomes the integral of u to the power of 10 du. And at this point, it becomes real simple. The integral of this becomes u to the 11th over 11 plus c. Let's reverse our substitution to finish up. 2 plus sine x to the 11th over 11 plus c. And we're all done. It's just like that. Okay? So, again, the rules are the same. Look for an inside function, and sometimes that can be the most difficult part. Finding the inside function, take the derivative of the inside function, then you got to look for what's the substitution that we're making. Remember, this is the substitution rule. Okay? Now, there are times, and this is when we learn our next technique of integration, that when you take the derivative of this, you won't find this piece in there. And that's then when we need another method to do it. I like to equate this to trigonometry when we were solving non-right triangles, using sine law or cosine law and determining which one we should use. We always started with sine law because sine law is easier to work with. And if sine law didn't work, then we would move to cosine law. Same thing here, we're gonna try substitution, because substitution is easier than the next method. If this doesn't work, we're gonna go on to the next method. Okay, but we gotta look for this first to see if it's gonna happen. And as you get better at it, you'll be able to look and see without even writing it down. Eventually we're going to wanna write it down, but you'll be able to see whether it's gonna work or not work in terms of that. All right, your assignment is gonna be a handout, so look on Connect for that handout and which question numbers to do. If you have any questions, ask. The next couple of videos that I'll make will probably be going over these questions. So ask your questions so I can go over ones that you're having trouble with, and then we'll go from there. And the other thing I want to point out is we've been doing indefinite integrals. These can be done with definite integrals as well. It doesn't change anything. Okay, we're going to get, if we had a definite integral when we got to the end here, instead of having a plus c, we'd be putting in numbers and getting a final answer. Okay, so they all work with definite integrals as well as what we're doing here with indefinite. Okay, so have a great day, do the assignment, ask your questions, and we'll see you again soon.